Hi dear students, let's see this question that came in KVPY 2020 SX Part 2 Physics paper. This was one of the fantabulous questions in this whole paper, and many students were simply, like they were stunned to see such a question. In fact, there is one thing happening in this question because of which some students even argued if this question makes any sense or is realistic in nature. So let's see what's happening over here. Basically, here a beam of neutrons is performing circular motion of radius 1 meter, as you can see, in the presence of magnetic field, which is not constant. There is some inhomogeneous or inhomogeneity in the magnetic field. Okay, that means magnetic field is not constant basically, and it has slight amount of variation. Okay, with respect to r. That means r is, you can say, radial distance. So we can say that if the you know uh, neutron is performing this type of circular motion, so of radius 1 meter, so if you go from r to r plus dr from the center, if you go from r to r plus dr, then there is slight change in the value of the magnetic field. Okay, so in fact, actually, we have to find that average variation only. We have to find the average change in the magnetic field over the variation of delta. That means how much magnetic field would have changed if we move by a distance of dr. Okay, when the value of r was 1. Okay, that means when r becomes r plus dr, so there will be change in the magnetic field. Okay, by the value of, let's say, dB. So we have to find the value of that delta b. Also, it's given that the speed of neutron is 54 meter per second. Mass of the neutron has been given to us, and the magnetic moment of the neutron has been given to us. Now, so as I was saying, some student thought ki how can magnetic field apply any force on on neutrons, because we know that to perform circular motion, any particle will require some amount of force, and neutrons are chargeless particles. They are neutral particles. It's a well-known fact. So how can magnetic field apply force on neutrons? So because of this amazing scenario, some students thought that if this question makes any sense. But let me tell you guys, the question is absolutely fine, and it is one of the finest questions that you can ever come across. So let's see what's happening over here. Basically, first let us try to understand that what are neutrons. Neutrons are overall chargeless particle, but if you will try to investigate the structure of neutron, then they are made up of quarks, something called as quarks. And quarks have got charge. So basically, a neutron has got one up quark and two down quark. A up quark has 2 by 3 charge of electron, positive, like magnitude wise it is 2/3 of electron, and value wise it's positive. That means you can say it's 2 by 3rd charge of proton. And a down quark has a negative 1/3 of electron. Okay, so basically overall neutron is a neutral particle, but uh, they are made up of something called as quarks, and quarks are not chargeless. They have some charge. So basically we can say that overall it is overall neutrons are neutral, but uh, like if you drill down, then they are not, like they have got some positive side and negative side within them. So it's like that. Actually, earlier it was thought that electrons are the smallest particles, and there is nothing small than electron. But as you might be knowing, or you might not be knowing, that there are further like particles which are smaller than electron have been discovered, which are called quarks. Okay, even other particles which are smaller than electron have been discovered. So the idea is that neutrons are made up of something called as quarks, and these quarks are chargeless, not chargeless. They have some charge. So overall neutron is neutral, but it has got some charge, it has got some quarks, and these quarks basically have their magnetic moment. Okay, they have some intrinsic magnetic moment. Also, they have got some orbital magnetic moment inside the neutron, and because of this magnetic moment, a neutron gets its magnetic moment. So although neutron is a neutral particle, it does some possess some magnetic moment. उसकी एक magnetic moment होती है. Okay, now let us see. Let's say कि एक जैसे I'll give you a different situation. Let's say एक bar magnet है. Okay, let's say एक bar magnet है. Now let's say this is the positive side of bar magnet. That means this is a north pole, and this is a south pole, there's a negative side. Okay, अब अगर इस बार मैग्नेट के इस बार मैग्नेट की एक मैग्नेटिक मोमेंट भी होगी फिर, लेट्स कॉल दिस मैग्नेटिक मोमेंट of the bar magnet as m. Okay, now if this bar magnet is present in a non-uniform magnetic field, if this bar magnet is present in a non-uniform magnetic field, then we know that this m dB by dr, this will be the value of the force that will act on this magnetic that will act on this bar magnet. ठीक है, ये जो एम डी बी बाई डी आर एक फोर्स लगेगा इस बार मैग्नेट के ऊपर. ठीक है, जैसे एक इलेक्ट्रिक डायपोल है, फॉर एग्जांपल एक इलेक्ट्रिक डायपोल है प्लस एंड माइनस, so this electric dipole will experience a force of P into d by dr, where P is the electric dipole moment and d by dr is the rate of change of electric field with respect to the r. Let's say this is r. Okay, so similarly when a magnetic dipole is kept in a magnetic field which is varying with respect to r, so m dB by dr is the magnetic field, magnetic force that will act on this bar magnet. Okay, which has magnetic moment m, which has magnetic moment m, right? Now you can think of this neutron as a bar magnet which has magnetic moment m as given in the question. So this is the magnetic moment of the neutron given in the question, and this bar magnet, you can say, which is a neutron actually, is moving in a circular motion. Okay, so we can say that this is the net centripetal force which is acting on this bar magnet, and it's providing the 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 force for circular motion. Okay, so basically we can say that, like, suppose this will be the scenario, like this is the bar magnet or this is the neutron which has got some magnetic moment. Okay, this is the positive side, this is negative side, like that. Okay, positive negative, like that. So because of this this in this situation, this neutron is revolving in a circular motion like this. Okay, so we can say that m dB by dr, m dB by dr is the net centripetal force, hence it should be equals to mv square by r. I hope you understood how I wrote this equation. Just like pde by dr, just like pde by dr is the force on an electric dipole present in a non-uniform electric field, similarly m dB by dr will be the force on a magnetic dipole which is present in a non-uniform magnetic field, m dB by dr. Okay, this will be equals to mv square by r, right? Now we have to find the value of dB. Okay, and this is mv square by r into dr upon m, where m is the magnetic moment. Now we can just put all the values. Mass of the neutron was given to us, which is 1.67 into 10 to the power minus 27. Okay, so 1.67 into 10 to the power minus 27. Speed of the neutron was given 54, so this will become 54 into 54. The dr, that means uh, the distance over which we have to find the variation, that dr has been given as 0.01 meters, so this we can put as 0.01. Okay, and divide by radius of circular motion is 1, and magnetic moment was given as 9.67 into 10 to the power minus 27. So 9.67 into 10 to the power minus 27. Now you can calculate this and you will get the value approximately equals to 5. When you solve this, this dB will approximately come out to be 5 Tesla. Okay, so this answer will be 5 Tesla. So as I told you, it's a very nice question, very nice question. Many students got stumped thinking that neutron is a charged particle. So how can a magnetic field apply force on a charged particle? So dear friends, as I told you, yes, neutron is a charged particle, but its magnetic moment is non-zero as is given in the question, and magnetic field can certainly apply a force on a particle which has non-zero magnetic moment. So this was the idea. I hope you would have understood. That's it. Thank you.